Hey everyone, welcome to Homeschool and welcome back to Class 11 Chemistry series. We are with the third chapter, that is classification of elements and their periodic properties. We have completed all about the classification. We discussed about Dobryner's triads, Newland's law of octaves, Mendeleev's periodic table, modern periodic table in detail, and we learned how we have classified modern periodic table into S block, P block, D block and F block based on electronic configuration, and also classification based on the chemical properties of elements, isn't it? And in my previous video, I taught you a beautiful trick to identify period number and group number of an element from the periodic table. So this is a very important question that you have to concentrate for competitive exam. So they give you some atomic number and they'll ask you to which group and to which period does it belong, or they'll give you electronic configuration and they ask you this question. So whereas to identify that, I taught you a simple trick in my previous video. So you can watch the video, link is provided in the description if you have not yet watched. And coming to today's topic, I am starting with the next aspects of the chapter. All about classification we have learned. Now we will study about periodic properties. So first, try to understand the meaning of the word periodic properties. See here, there are certain properties of an element that gets repeated in a group after some atomic numbers. So such properties are called periodic properties. I mean to say, suppose you have lithium, its atomic number is 3. So below lithium you have sodium, its atomic number is 11. There are certain properties which looks similar as that of lithium. And when is our sodium coming? Sodium is coming after some atomic numbers. Between lithium and sodium, you have 8 other elements. So you have beryllium, you have boron, you have carbon, you have nitrogen, and after some atomic number, you have got an element where in that element you will see a character getting repeated. You will see a physical and chemical property getting repeated which looks exactly similar to the above element. That particular property may be similar to the above element. So that's why we say all elements which come in a same group will have same property. So that particular property gets repeated as you go to the bottom, right? So, and how it got repeated? After certain atomic numbers. So after some atomic number, you have got this atomic number, where in this particular element, you have the same property, you have a property which is common to lithium. So such properties we are going to discuss, and those properties we mainly call it as periodic properties. And you know what? These periodic properties vary in a periodic table. As you go from left to right in a periodic table, the property may increase, the property may decrease, and when you go from top to bottom in a group, there are certain properties that can increase or decrease. So there is always a slight variation in these properties. So we are going to discuss about such periodic properties and their variation in a periodic table. Okay, so if I have to list out those properties, it is atomic size is the first and very important property, or we can also call it as radii. Atomic, radii, radius, atomic size, all same. Okay. Second one is ionization enthalpy. So this is another very important property on which the chemical properties of elements depend. So actually based on these properties, the chemical reactions or the physical properties depend on. Right? So ionization enthalpy is one such very important property that you will observe with element. And third one is electronegativity. And fourth property, electron gain enthalpy. So this is also one such important property that you have to study about the element. And there's lots of difference between electronegativity and electron gain enthalpy. All that differences we will try to study in detail, right? And next one is electropositivity. We say something called electropositivity. Electropositivity is nothing but metallic character. And we will also talk about valency, you know. So all these are periodic properties, okay? And there is certain variation in the periodic table as you go from one group to another to another, you know, there is a variation, right? So all those variations and what are the reasons for those variations, everything we have to study. And in this class, I am going to cover everything about atomic size, radii. Okay, we will discuss what is atomic size, what are the different types of atomic radii are there actually, and ionic size we will discuss, and most importantly, important topic for competitive exams is isoelectronic species. So to identify isoelectronic species, I will teach you a beautiful trick. So watch the video till the end. Definitely it will give you 100% benefit, right? So let's go into the topic atomic size or atomic radii. Let's understand the meaning of the word atomic size, which is also called as atomic radii. Okay. See, we all know atom will have a nucleus at the center and it will have many shells around this. Electrons are present in the shells which are present around the nucleus, right? So atomic radii is nothing but it is the distance between this nuclei and the last shell. Okay, so distance between the nuclei, let me write it here. It's very important to understand distance between what and what? Between nuclei or nucleus and last shell, or we will also call it as valence shell, right? So in valence shell or in last shell, our valence electrons are present. So it is the distance between the nucleus and the valence shell. Okay, so instead of calling as last shell, it's nice to call it as valence shell where valence electrons are present. So that distance we will call it as atomic radii. And this atomic radii to measure is very difficult. Okay, why? Because see, extracting single atom itself is practically not possible. If you want to measure this distance, you need to extract one single atom from a substance or element. Is it possible to extract one single atom? It's not possible practically, right? So that is the reason, you know, measuring this distance, that is the distance between nuclei and the last shell, is practically not possible. That is the reason we are taking this distance with the help of several bonds. Okay, so by one atom can combine with another atom and make attractions. You will observe attractions between the two atoms, which we will call it as bonds. We have covalent bond, metallic bond, right? Ionic bond. There are so many types of bonds that can be formed when one atom combines with another atom. So with the help of these bonds, we are trying to find out this particular distance. So we have different types of bonds, isn't it? So we have different types of atomic radii. Okay, so this concept is very important. And now I am talking about different types of atomic radii. Okay, so why we have different types of atomic radii? It's because atoms can combine with one another by various types of bonding. Since we cannot practically extract a single atom and then measure this distance, we are measuring this distance indirectly by observing the type of bonding between the two atoms. Okay, so we have different types of atomic radii. So the first one is covalent radii. So this is really very important to measure the atomic size of many elements. We have considered covalent radii. Okay, so let's discuss everything about covalent radii in detail. Second one is metallic radii, and third one vanderwaals radii. So this vanderwaals radii is used in case of noble gases, right? So vanderwaals radii. So let's discuss all the three in detail. First and foremost, covalent radii. See guys, this covalent radii can be used when two atoms combine with each other to form a covalent bond. So how is a covalent bond is formed? Imagine you have hydrogen molecule where I want to find out atomic size of one hydrogen. So my aim is to find out atomic size of one hydrogen atom. So I take the help of H2 molecule. First, I'll try to identify how these H2 molecules are formed. You studied in your basic classes how covalent bonds are formed, right? It is by overlapping of atoms. See, this is a nucleus. This is the first shell where one electron is there. So this is hydrogen atom 1, and this is another hydrogen atom where electron is there, right? Let me write this electron this side. This is hydrogen atom 2. When they overlap, this is how the atoms overlap, and here your covalent bond is formed. Sharing of electrons takes place. That itself we will call it as covalent bond. Okay, so this is the nucleus of first hydrogen atom. This is the nucleus of second hydrogen atom. So this is what we mean by H2 molecule. Okay, so this is one hydrogen atom, another hydrogen atom. They must have combined, overlapped with each other, something like this. So sharing of electrons took place. So hydrogen molecule is formed. So this is the theory behind formation of covalent bond. Okay, and once they are covalently bonded with each other, once they have overlapped with each other, you know what? This distance, the distance between nucleus of this hydrogen atom and nucleus of other hydrogen atom, this distance we will call it as internuclear distance. So it is called as internuclear distance. Covalent radii is nothing but half of this internuclear distance is called as covalent radii. Okay, see, if you make this distance half, almost it can be equal to the size, radius of this atom, right? See, anyway, actually covalent radii is smaller than actual radius, but then it can be considered as one of the type of atomic radii. Okay, so half of the internuclear distance between the atoms which have covalently bonded with each other is called as covalent radii. Okay, so let me write its definition. Half of, this is important, half of internuclear distance between atoms which are covalently bonded is called as covalent radii. Okay, so when atoms overlap with each other and the internuclear distance half is called covalent radii. For example, here let me give an example. H2 molecule has the internuclear distance of around 72. Okay, so what is the atomic radii? atomic radii of single hydrogen atom is 72 divided by 2, half of the internuclear distance. So how much is your answer? Your answer is 36 picometer. Right? So this is how you will find this atomic radii is what type of radii? It is covalent radii. Okay, this is the internuclear distance in hydrogen molecule. If I have to find covalent radii, it is 72 by 2. It is the half of the internuclear distance will give you covalent radii. So this is how indirectly we are trying to find the distance between the nuclei and the last shell. Okay, it will not be exactly similar to the actual radius, but then approximate values we will get. Okay, so this is how the size of atom was determined. I mean, atomic radii was determined. Similarly, let's go for metallic radii. See, now let's go for second type of radii, metallic radii. So usually metallic radii is designated with Rm. Okay, covalent radii Rv. R means small r is nothing but radius. Okay, you see here when we have some metals like iron, copper, silver, all these are metals. So these elements will have crores and crores of atoms, right? So between one atom and another atom, there is an attraction called metallic bond. Okay, see here. This is one atom, this is another atom, just they have touched with each other. Attraction between them is metallic bond. Okay, and the distance between the nucleus of this atom and this atom, as usual, we will call it as internuclear distance. So metallic radii is nothing but half of that internuclear distance. Okay, say let me write it here. Half of the internuclear distance between the atoms which are bonded by metallic bond is called as metallic radii. So covalent bond is formed by overlapping, right? Whereas metallic bond is formed like this. They just touch with each other, two atoms. Okay. So actually speaking, half of this distance will be the actual radius of one single atom. Right? I told you, covalent radii, if you consider, it is actually much smaller than actual radius of the atom, right? But here, this metallic radii will be exactly equal to the actual radius of atom. Okay, so depending on the type of bonding, we have these radii. So half of the internuclear distance, the distance between the two nuclei between the two atoms which are bonded by metallic bond, half of that distance we call it as metallic radii. Okay, so hope you are clear with the difference between covalent radii and metallic radii. Now we will go to another important type of radii, vanderwaals radii. That's a third type of radii. Observe carefully, guys. These vanderwaals radii we consider only for noble gases. Okay, see, for all other elements, to talk about atomic size, we consider either covalent radii or metallic radii. But to talk about the size of noble gases, we always consider vanderwaals radii. So what is this vanderwaals radii? So imagine, this is one molecule of neon. Okay, so the best example for noble gas is neon or helium. Okay, so this is one neon molecule. And how did this neon molecule formed? This is one neon atom. Okay, this is another neon atom, so which have covalently bonded with each other. Okay, so this makes one molecule of neon. There is another molecule nearby. This is another molecule of neon. Okay, so actually both of them have certain attractions between them. We call those attractions as van der Waals attractions. So about the different attractions between the atoms and molecules, you will study in the chapter states of matter. Okay, so just as of now, understand between this molecule and this molecule, there is a weak attractive force which we will call it as van der Waals attraction. Okay, see now observe here. See, this is the nucleus of this atom. This is the nucleus of this atom, right? And anyway, there is a nucleus for this atom, there is a nucleus for this atom. But you know, here the distance between the nucleus of one of the atom of one molecule and another atom of another molecule, you can observe. I'm not talking about this distance. I'm not talking about this distance. This is one molecule, this is another separate molecule, but the distance between one of the atom of this molecule and one of the atom of this molecule, so this distance is what we will call it as internuclear distance. Okay, so this is our internuclear distance here. Okay, right? And half of this internuclear distance, okay, so half of this internuclear distance is called van der Waals radii. Okay, RV I will write. Okay, so RV I can write, van der Waals radii. Right? So you are getting my point, right? So understanding a concept is very important. So half of this so is this radii, it's much greater than actual atomic radii. If you consider this atom, its radii is this much, but van der Waals radii, if you consider for this, it is this much. See, its actual radius is this much, but van der Waals radii, if you consider, it's much bigger. Right? So van der Waals radii is always much bigger than actual atomic radii. Right? So this is one molecule, this is another molecule. Atom of one molecule, atom of another molecule. Between them, half of the internuclear distance is called as van der Waals radii. Okay, so we understood covalent radii, metallic radii and van der Waals radii. Okay, so any one of these radii we can identify and consider it as atomic radii. Okay, fine. And now let's summarize, a van der Waals radii. Let me write, van der Waals radii is much bigger than, metallic radii. This is important for competitive exams. And this is much bigger than covalent radii, right? Covalent radii is always smaller. Its value is always smaller, right? Compared to metallic radii. Van der Waals radii value is always higher. So that's why for noble gases, we consider van der Waals radii as atomic radii or atomic size. So we always say noble gases are bigger in size. Okay, we say noble gases are very big in size. Why? Because as their atomic radii, we are actually considering van der Waals radii. Van der Waals radii is actually speaking, you see, half of this internuclear distance I am considering as size of this atom. It's actually much bigger than actual radius of an atom. Right? So hope you are clear with three types of radii. So this way we can identify the atomic radii of a particular atom in a particular element. So now let us talk about how this atomic radii varies in a periodic table. I mean, from left to right if I go, whether this property increases or decreases. Why? And from top to bottom if I go, what happens for this property? As I go from element to element from top to bottom, will the size of an atom increases or decreases? Okay, so all that we will discuss now. See guys, everyone observe carefully here. This atomic size, as we move from left to right in a periodic table, our atomic size always decreases. So this is really a very important thing. Actually, every other properties depend on size. So you need to carefully understand this concept. Atomic size decreases. So what do you mean by this point? If I take second period elements, I have lithium, beryllium, boron, carbon, nitrogen, oxygen and fluorine. You forget about noble gases, because in case of noble gases, I told you we will consider vanderwaals radii, whereas vanderwaals radii is very much bigger type of a radii, right? Noble gases are quite larger in size, we say. So except that these are the elements that come in a second period. So as I move from lithium to fluorine, what happens is the size decreases. Say normally everyone thinks that as atomic number increases, size will increase. But no, in this case it is not true. You see here, lithium's atomic number 3, beryllium 4, and this is 5, this is 6, this is 7, this is 8 and this is 9. Atomic number is increasing gradually, but atomic size decreases. So why is the reason why atomic size decreases? It is because the nuclear charge, I am giving you a reason, this is really very important. What happens here? The nuclear charge increases. So this is what your answer. So what do you mean by nuclear charge? It is the total positive charge of an atom. So which particles are responsible for positive charge? Protons. Where are the protons present? Inside the nucleus, right? So let us see. In case of lithium, say this is the nucleus of lithium. You have 3 protons, and whereas outermost electrons are present in the third shell, isn't it? So in the outermost shell you have like 1 electron, right? Say what is its electronic configuration? 1s2, 2s1. So 1s is first one. So this is a nucleus, this is a nucleus, first shell, second shell. So in the second shell 1 electron you have. Coming to beryllium, in beryllium nucleus has 4 protons and the outermost shell has 2 electrons. Coming to boron, in boron you have nucleus have 5 protons, whereas outermost shell has 3 electrons, right? Coming to carbon, you have 6 protons, first shell, outermost shell has 4 electrons. You see here, as you go from lithium to fluorine, outermost shell is your second shell only. So your number of electrons are increasing as you go from lithium to fluorine, but those electrons are there in a second shell. Shell number is not increasing. All electrons are present in a second shell only. I am talking about valence electron. What is increasing is nuclear charge. Number of protons are increasing. So as number of protons increases, what would happen? This nucleus tries to pull the outermost shell towards itself. Okay, imagine in carbon outermost shell is here. So this shell will get pulled more towards nucleus. Okay, so you will find more attraction between nucleus and the last shell when more number of protons are there inside the nucleus. Okay, so what happens as a result of this? Since there is a more attraction between nucleus and last shell will slightly move towards nucleus. So when a last shell is slightly moved towards nucleus, automatically radius decreases, the size decreases. Okay, because outermost shell is same in all the elements of second period. Outermost shell is your second shell, outermost shell is same, but number of protons are increasing. As a result, attraction between the nucleus and outermost shell increases. Because of that, outermost shell is pulled more and more towards nucleus as the number of protons increases. Okay, so that way we say the size always decreases when we go from left to right in a periodic table. Size decreases. Remember this. Why? Because nuclear charge increases, that is the number of protons inside the nucleus is increasing. Fine. And the next thing is, next point, from top to bottom what will happen? From top to bottom in a periodic table, that means let me take the first group: lithium, sodium, potassium, rubidium, cesium. So what will happen here is the size will increase. Okay, atomic size increases. This is really very important. Lithium's atomic number is 3. Sodium's atomic number is 11. Potassium's is 19. So you would ask me, here also atomic number increasing. That means the number of protons inside the nucleus increases. Nuclear charge increases. If nuclear charge increases, what should happen? The size must decrease, right? But here what is happening? See, lithium, your outermost electron is in second shell, whereas sodium, your outermost electron is there in third shell. Potassium, your outermost electron is there in fourth shell. See, the number of shells are increasing. Okay, so outermost shell is somewhere very far as you go from lithium to cesium, right? So the shell number increases. So here there is no point in increasing nuclear charge. Even if the nuclear charge is increasing, since the shell number is increasing, atomic size will increase. Here what happened? The last shell is same in all the elements. Protons increasing, so attraction between the nucleus and last shell increases. Last shell will move slightly more near to the nucleus, so atomic size decreased. But here what's happening from top to bottom? The shell count is increasing. Lithium has 2 shells, sodium has 3 shells, potassium has 4 shells, and rubidium, outermost electron is there in 5th shell. Outermost shell is increasing. Atomic size is after all a distance between nucleus and the last shell. When the last shell is increasing, it is there very, very far from nucleus. So automatically atomic size will increase. Though nuclear charge increases, it doesn't matter. Atomic size increases because what is the reason here? Because number of shells are increasing. Number of shells increases. This is the reason, guys. So very, very important. Along with the reason, you must learn. See, from left to right in a periodic table as you go, size will decrease. What is the reason? Reason is nuclear charge increases. From top to bottom in a periodic table, atomic size increases. What is the reason? Number of shells increases. So this is really a very, very basic point one must remember, right? So this is all about atomic size or atomic radii. Now let's talk about ionic radii. See, what may be the difference between atomic size and ionic size? Atom is neutral. Ion is, it has some charge, positive or negative charge. Let's understand why these ions are formed, right? For example, right, see, we all know there are 2 types of ion. One is cation, the other one is anion, right? For example, I will take sodium, whose atomic number is 11. If I have to write its electronic configuration, 1s2, 2s2, 2p6, 3s1, right? See, if it can lose this electron, it will achieve noble gas electronic configuration. It becomes stable. So this particular sodium loses. It will lose 1 electron and it will become Na+. So now this Na plus has electronic configuration 1s2, 2s2, 2p6. So since it has lost, so why we have put positive charges? Because we all know our sodium, right? Inside the nucleus, it has 11 protons which are positive, and outside the nucleus in different shells you have 11 electrons which are negatively charged. So in sodium atom there are 11 protons with positive charge, there are 11 electrons negative charge. So number of positive charges were equal to the number of negative charges. So what happened? The atom became neutral. But now what happened here? Sodium lost 1 electron. Now it has got only 10 electrons in various shells. Now, can I call this as a neutral atom? No. Positive charges are more, negative charges are less. So, this particular atom will have a positive charge. So, Na plus. Why do we write Na plus? Always when something on losing electron, it gets positive sign. Because on losing electron, your proton count is more. Protons are positively charged. Since proton count is more, see 11 protons, 10 electrons only after losing 1 electron. Proton count is more, right? More positive charges are there. So we put positive charge on sodium. So normally we say whenever something loses electron, that gets converted into cation, we say. So positive ion is always called as cation. Okay, fine. And similarly, how do you get a negative ion? Say fluorine is there. Atomic number 9. If I have to write its electronic configuration, 1s2, 2s2, 2p5. See, if 2p5, right? Yeah. If it gains 1 plus 1 electron, if you add, it will have noble gas electronic configuration 1s2, 2s2, 2p6, isn't it? So after gaining 1 electron, this F is not a neutral atom. Now it has become F minus, which we will call it as anion. Okay, so why this negative charge? See, in the nucleus of fluorine, you have 9 protons. But 1 extra electron has added. Initially, there were 9 electrons. But now you added 1 electron. Only then it gets stability, right? So altogether you have 10 electrons. So negative charges are more than positive charges. So as a whole, this fluorine atom is becoming negatively charged. So now it is no more a neutral atom. It has become charged atom, which we call it as ion. Negative charge if it is there, anion we say. So this is how cation and anion formation takes place. Okay, and always remember cations are always smaller than parent atom. Okay, whereas anions are always bigger than parent atom. This is really very important. That means if I ask you between F and F minus, which one is bigger in size? See, F minus, more electrons are there, right? If more electrons are there, more repulsion you will observe. Since more repulsion is there, you will not expect so much attraction from nucleus and outermost shell. Shell goes away and away. So atomic size increases. So that way we say, always anions are greater in size than parent atom. Say now here, between sodium and Na plus, which is greater in size? See, it has lost electron, right? On losing electron, you got cation. Number of positive charges more. Just now I told you, as the number of positive charges, protons increases in the nucleus, the last shell moves more and more towards nucleus because of more attraction between nucleus and the last shell. When the last shell is pulled towards the nucleus, atomic size decreases. So definitely here, Na will have greater size than Na plus. So that's why I told you cations are always smaller than parent atom. Anions are always bigger than parent atom. Okay. So now on this concept, definitely you can expect few competitive questions. Say for example, you have I plus and I minus. Iodine neutral atom, iodine cation, iodine anion. Okay, so among them, which one is bigger? Or they'll ask you, see the question is, arrange in decreasing order of their size. Okay, so size of ion is ionic size, size of atom is atomic size, whatever. So you have to arrange these species in the decreasing order of their size. So decreasing order means bigger size to smaller size. So who is bigger here? I already told you anions are bigger than parent. This is parent iodine, neutral one. This is cation, this is anion. Always I minus is greater than neutral one. This is greater than I plus. So this is your correct order, right? So this kind of questions you can expect for your competitive examination. So this is how questions can be asked on ionic size. You should always know anions are bigger because more electrons, more repulsion you will observe between electron. Shell will go outer and outer. So you will not have enough attraction between nucleus and outer shell. Okay, so shell goes away and away, so size increases. Whereas in cations, more positive charges. So shell moves more towards nucleus. So size automatically decreases than expected. So cations are always smaller in size, anions are always bigger in size than neutral parent atom. Okay, so that's all about ionic size. Now let us talk about very important concept, isoelectronic species. See guys, just like isotopes, isobars, isotones, we have something called isoelectronic species. So isoelectronic species in the sense those species, it can be ions. Most of the time it can be a cations or anions, okay, or combination of cations or anions. So those species, especially it is always a charged or uncharged. I cannot specifically say only charged. So charged or uncharged species with same number of electrons. This is important. Same number of electrons is called isoelectronic species. For example, just observe these ions F minus, O minus 2, N minus 3, Mg plus 2, Al plus 3. Okay, so here atomic number of fluorine 9, atomic number of oxygen 8, atomic number of nitrogen 7, atomic number of Mg 12, atomic number of Al 13, right? So what is common here? Atomic numbers are different, but you see F minus means what? 1 electron extra. So 9 plus 1, there are 10 electrons. Oxygen, 8 electrons were there. Now minus 2 means what? 2 electrons extra. Minus anions. How anions are formed? Always by the addition of electrons. So minus 1 means 1 electron is added to neutral fluorine. Minus 2 means 2 electrons are added to neutral oxygen. Okay, so oxygen neutral one already has 8 electrons. 8 plus 2, 10. So 10 electrons. Nitrogen already has 7. Minus 3 means 7 plus 3, 10 electrons. So plus means what? It has lost electrons from the existing one. So Mg neutral had 12. Plus 2 means remove 2 electron. If you remove 12 minus 2, if you do 10 electrons. Say aluminium, 13 electrons it had, but Al plus 3. In Al plus 3 you will have 10 electrons. Plus means what? Losing electron. Okay, say all of them have 10 electrons. So those species with the same number of electrons are called isoelectronic species. So all these I can say isoelectronic species. So what are isoelectronic species? Different elements or different ions, different atomic number but same number of electrons are isoelectronic species. So you must completely understand the concept what actually we mean by isoelectronic species. And after this you have to decide which ion has more size or less size, okay, among isoelectronic species. You can't just decide based on atomic number. See, actually fluorine, oxygen and Mg and aluminium comes in the third period and these are coming in the second period, and they don't belong to a same group, right? So how would you judge the size here? Always remember, in case of isoelectronic species, okay, so in isoelectronic species, okay, as nuclear charge increases, as nuclear charge increases, so when does the nuclear charge increases? Atomic number increases. Okay, so as nuclear charge increases, that means as atomic number increases, atomic number increases, size decreases. Size decreases. We know whenever nuclear charge increases, what would happen? Attraction between outermost shell and nucleus will increase. As a result of that, outermost shell will move more and more near to the nucleus. So that way size decreases. So here, when does the nuclear charge can increase? Atomic number increases. So just think of, connect size and atomic number. In case of isoelectronic species only, you can't apply this for neutral elements or whatever it is. When they are having same number of electron, among them, if you have to decide who is more in size, who is less in size, then you can apply this. So this is what your trick to identify the size in isoelectronic species. More the atomic number, lesser is the size. So now can you decide who is lesser in size? Which one has less ionic size or atomic size? It is, just check the atomic number. Maximum atomic number is for Al plus 3. So Al plus 3 is least in atomic size than Mg plus 2. Next smaller one is, this one, F minus. Next least size is O minus 2. Then the highest size, ionic size, you will find for N minus 3. So N minus 3 is bigger ion. Al plus 3 is smaller ion in these isoelectronic species. Okay, so this is how you have to identify which ion is bigger, which is smaller, as long as they are isoelectronic species. Okay, so this trick can help you out in solving many questions, almost all the questions relating to isoelectronic species. So what is important is, first you should know the definition of isoelectronic species, then you must able to identify whether the given things are isoelectronic species or not. Then if any question is asked based on the size, they will ask you, arrange them in the increasing order of their size or decreasing order of their size. So then size related things, if you want to answer, just remember, more the atomic number, lesser is the size. More the atomic number, lesser is the size of isoelectronic species. Okay, so this is really very, very important, right? Okay, so that's all about today's video, and in my next class I will come up with one more important periodic property, that is ionization enthalpy. Till then, revise the concept, take care, and do subscribe our channel to learn the concepts in a easiest way and in a detailed way. Thank you so much.